just kind of reviewing here. We had a 91 kilogram refrigerator on a ramp. Refrigerator begins to slide when it's raised to 34. What's the coefficient of static friction? So let's redraw this. Okay, thanks. I wasn't recording. Oops. So we've got the picture drawn. Let me undo what I just did. We did a sum of forces on the y, so we know that the normal force is going to be equal to the negative of mass gravity cosine theta. And looking at the x-axis, we have force of static friction up the ramp. We have force of gravity on the x down the ramp. So that's all we've got. And at the moment they begin to slide, those two things become equal. So we have Fgx f of s, and we have negative of mass gravity sine theta equals fs. So the big thing to remember here, and this is where the kind of breakthrough came, last year, in terms of like having an aha moment. When you look at this picture, so we have to think about those positives and negatives. And we can impose the Cartesian coordinate system. That's probably the easiest. The weird part that gives us is that the force of static friction, and we usually think of forces of friction as negative because they are opposing motion, that gives us a positive force of static friction. Okay? So when we get into what's going to happen next, wait, is this exciting? When we get to the point where this is, maybe this wasn't the one where we had an issue. This wasn't it, was it?
The angle I have on my paper for the one we did was 30, not 34.
No, this was it. No, it was the next one. It was, yeah, you're right. 30.
Okay, so this one there was no disagreement on. Okay, well, I'll still use it as a ramp to talk about what we're going to come to. So we have mu s then equals fs over fn, and we know that that's going to be negative mg cosine theta over negative mg sine theta. We've been kind of, and it's my fault, I've been real sloppy about the signs on this. When we get into like, oh, but then the coefficient of friction would be negative. I'll disregard it. I shouldn't be so lazy and so sloppy. What we want to think about, because in this work we're doing a lot of substitutions, so we're creating a lot of expressions and doing, it's heavy algebra too, and it gets more interesting even. But what we want to think about is looking back to our image. If we're gonna be strict with Cartesian coordinates and we're going to do substitutions, we want to think about what the value that we're substituting for would be in terms of sign. So, here, if we're strict with Cartesian coordinates, normal force is going to be positive. So when we are substituting something in for a positive, it should be a positive number. And here, if we have the negative of mass gravity cosine theta, it is. So our algebra has not failed us here. It's the negative of a negative, it's a positive. It's a tiny little detail. In the next problem, that's where it becomes an issue. And I guess that was from the chapter review, wasn't it? That we did another one. So let's go back to that. Okay, this one was where we talked about the trick of like, ooh, magically it's tan theta. Okay, the other one, number 38, was the one where we had two different answers coming up, and I know why. Jason was right, and I can prove it. So on this one, number 38, we have, it's a 30-degree ramp. Box is sliding down it and has an acceleration of 1.2 meters per second squared. We have f of g, f of gy, f of gx, force of kinetic friction, and I got to move this somewhere, and normal force. Very badly drawn. I would hope you would do better than me. I slopped that all together. Maybe I can fix that. Okay, a little bit better. That's right. So we're asking for the coefficient of static friction, mu k, which is equal to Fk over Fn. And we know that the acceleration is in what direction? Down the ramp. Yeah, whichever way pointing makes sense. It's down the ramp. So the ma, which is represented by the mass of the object, and the acceleration has got to have the same sign as what? The force of kinetic friction or the force of gravity on the x?
Can you repeat the question one more time?
Sure.
Rephrase that.
Yes. So we know that, here, let's do sum of forces on the y. It's 0. It is Fn plus f of gy. Fn equals negative f of gy. Great. Everybody's happy on the y-axis. On the x-axis, it's equal to mass times acceleration, because that's the axis on which this acceleration is occurring. It's really helpful, just like when we break out vectors. I'm going to do this. That mass acceleration is down the ramp, which means it's going to have the same sign. So you have two forces acting on this object. You have f gx. You have f of k. Which direction is f of gx acting? Down the ramp. Same little arrow as the ma. Which direction is the force of kinetic friction acting? Up the ramp. So that mass acceleration has got to have the same sign as which one of those two? F of gx. And that's where the problem was. So you have to look at, in a case like this where something's moving, that mass acceleration, in other words, what we're saying is the net force on it, is down the ramp. But if you do some kind of reminder for yourself on this, it really helps. So now we can go ahead and solve. So we've got an expression for f of n. We need an expression for f of k. So we have ma minus f of gx. But what we have to remember is this is a negative minus a negative, if we're going to be strict about Cartesian coordinate systems. So that's equal to f of k. We can go ahead and ma minus mg, and this is a negative number, mg sine theta equals fk. Let's move this up just a little.
Negative mg sine theta.
Well, hold on. Fn equals the negative of mg cosine theta. So we're now ready to put those values into our expression for mu k. So mu k equals, well, fk is equal to ma, which is going to be a negative number. Okay? This is going to be a negative number. And this is the system that me and the two Wunder students in physics last year came up with. And it worked. You know, I'm constantly looking for tricks that will allow me to not make feeble-brained, stupid mistakes, and this is one of them. So when I'm doing a lot of substitutions or I've got a situation like this, I tend, same thing as my trick of putting little arrows over the directions on non-perpendicular vectors or multiple forces. I'll put a little sign over that, or you can do a little arrow, whichever, if you're using the arrows as proxies. And we know that this number has to be negative. It's going to be, because we're using negative 9.81 meters per second as gravity. So then I'm subtracting that mg sine theta, and I know that that's a negative, so it's a negative minus a negative. In other words, the magnitude's going to be less than one of them. And then here I've got negative mg cosine theta. Now here's a question. Does it matter that we know the mass of this object? Nope, because mass is going to cancel. So even if we were given this problem without mass, we can solve it very easily. Yeah?
Can
Sure, absolutely. And let me shrink a few things. And we can factor out mass from that first. Excuse me. Thank you. Excuse me. Minus g sine theta over mass, gravity, cosine theta, and then we just cancel the mass. So we have acceleration, which we're remembering as a negative because it's down the slope. It's in what we're calling a negative direction in terms of Cartesian coordinates. So negative acceleration minus g sine theta over g cosine theta. And you cannot do, I don't believe you can do the tangent trick here. I always have to prove that case to myself, and I'm pretty sure without proving it that I can say, no, you can't do the tangent trick. So let's go ahead and get the answer, and I think we should all come up with the right thing. Things like that, not being given mass, are the other reason I've been saying all along, don't solve for numbers, don't solve for numbers, don't solve for numbers. In a lot of cases, you get to a point where you can't. So you have to be able to get it down to a single expression, simplify as much as you can, cancel as much as you can, eliminate as much as you can, because that's what will allow you to solve problems that are missing some pieces. The negative didn't go away there, did it? It shouldn't have. Okay. Okay, so mu k is 0.436. And you should all get that now. But that was the issue. If we were treating this acceleration as a positive, we get the wrong magnitude. So things to just be real careful about. Questions on that? Okay. Okay, so.
It's an oboe.
Ha ha ha.
Wow.
For an object that's on a flat surface that's having applied force applied on the x-axis, normal force equals force of gravity, right? Yeah. So you look at this and you go, okay, well, Fn equals Fg. Cool. That's fine, because those are the only forces on the y-axis. The minute we take this and do that with it, you have an additional force on the y-axis. This is just like the problems where you have somebody pushing down on a box and suddenly you have an additional force on the y-axis. In this case, the normal force is going to be greater or lesser than the force of gravity? Equals 0 equals Fn up, F applied up. Whoops, not F of gy, just F of g. The normal force greater or lesser than the force of gravity on the y-axis? Less. Because the force of gravity, in addition to the force that is being applied on the y-axis, are equal to gravity. So the sum of those two forces equals gravity. Here's the way to think about this. If you had, you've done the classic horror movie teenager dumb thing, and you've gone into the scary house with the sketchy rotted floor, and this is a physics horror movie, so you're being asked to drag a box of bricks across the sketchy floor. And if it collapses, it's the worst kind of horror movie. You should totally make one. And because you've got iMovie on your iPads, go. In order to keep that box if you're able to stand off the sketchy floor and you have to pull it across, to keep that floor from collapsing, what do you want to do? You want to pull up on that rope as much as possible, because by doing so, you're lessening the amount of normal force that the surface has to provide to counter gravity. You're doing something that helps the floor.
Really?
Yeah, of course. Yeah. We can think about a lot of these in real-life scenarios for real-life problem solving. But that's the key there, is making sure that you don't take for granted that normal force is equal to force of gravity. It isn't if there's another force on the y-axis. Okay?